So our next, I guess, next company presenting, I should say, is going to be ARM. We have two speakers today because, again, they've got a lot to tell us and they're going to kind of divvy it up. And the first speaker is Stefan Rosinger. He's the Director of Product Management, and he is responsible for the delivery and quality of the Cortex-A, R, and the M series. And we have Jinson Koppanalil. He's a distinguished engineer over at ARM. He's been there for 18 years, and he's had a variety of roles from architecture to physical design, and he received his master's from NC State. So thank you guys for coming, and I know I look forward to your announcement as well as everybody else here.
My name is Stefan Rosinger. As Akash was saying, I'm the Director of CPU Product Management in the client line of business of ARM, looking after ARM processors. And today I'm joined by my colleague, Jinson Koppanalil, who is, as Akash was saying, distinguished engineer, key member of our CPU Design Center in Austin. And today we're really pleased to give you guys an overview about the latest developments on the ARM CPU side, as well as share some really exciting new developments. So let me have a quick look at what's going on today in the smartphone market. Now, as you know, the smartphone really is ruling essentially our lives. It basically is getting more and more complex, and the smartphone we have today, won't be the smartphone we'll have tomorrow. New technologies like 5G, machine learning are just some of the catalyst drivers that we do see as driving new use cases for the smartphone. Now, so what do consumers really looking to get from the devices? Well, actually, there's a couple of interesting use cases. Obviously, they're all somewhat conflicting. For one, they're looking at this immersive experience and essentially the high performance that we need, but also they really want uncompromised productivity. And they all want this for really the all-day battery life, or actually even better battery life, right? So in summary, what we need to cover those use cases is essentially higher performance, high peak performance, improved sustained performance, but also really this unparalleled power efficiency. And with this year's lineup of IP that we've launched in May this year, as part of the 2020 Total Compute solution, we're really unlocking that new class of experiences where we deliver the peak performance as well as the sustained performance needs and the area and power efficiency. So that's really the lineup of the Cortex-X1 CPU, the A78 CPU, and the A55, as well as, of course, accompanied with our GPU and NPU offering. Now, this year was special because we've not just launched new IP products and new total compute solutions, but alongside of the overall IP portfolio, we've also launched a new program called the Cortex-X Custom Program. Now, this program is really special for us because it's a really special collaboration between ARM and our partners to build CPUs that are just really specifically tuned to their needs. Now, what does it make so special? Well, key is we actually in the CXC program are basically pushing forward and much higher on total performance than we would normally do on a standard roadmap. Now, this is really a truly landmark moment for the Cortex CPUs. And I think we will deliver essentially what our partners really want to differentiate and compete, not just in the smartphone form factor, but maybe even beyond that, right? And that's really important for us to enable our partners to really establish and get their designs that they really want. And we cannot wait to really see the first silicon in products in next year. Now, the first CPU that we've launched alongside the CXC program is the Cortex-X1. So the X1 really is kind of the first step in that program, where essentially we're pushing single thread performance as hard as basically we can from a CPU design perspective. Now, to give you a bit more technical details about the X1, I have Jinson here, and with that, I want to hand it over to Jinson to give you a bit more technical detail.
Thank you, Stefan. So as Stefan mentioned, X1 is the most powerful Cortex CPU to date. At a high level, it is a wider and deeper out-of-order machine and is built for peak performance. Although it's a larger design, we have made sure there is no impact to the maximum frequency capability of the design. So I'll walk you through the microarchitecture and sort of highlight the key improvements compared to the Cortex-A77, A78 pipelines. So starting with the branch predictor, We have an L0 BTB, which provides fast single cycle prediction of the next taken branch. So this is a 0 cycle pipeline. So in X1, the L0 BTB is 50% larger, and that reduces the overall branch prediction latency. Also, if you remember in Cortex-A77, we introduced a performance feature called the MOP cache. MOP cache is a decoded L0 instruction cache, and it is smaller but higher bandwidth compared to the L1 instruction cache. So in Cortex-X1, we have increased the bandwidth out of both these caches. So when you compare the bandwidths, MOP cache can now deliver 8 MOPs every cycle, and instruction cache can deliver 5 instructions every cycle. We have also doubled the MOP cache capacity to 3,000 entries to increase the coverage. Now let's look at the core. So we have increased the rename dispatch width from 6 to 8 instructions per cycle. So that is a 33% increase in dispatch bandwidth. We've also increased the out of order window by 40%. So both these changes help expose more instruction level parallelism and performance as a result. On the FP and SIMD pipe, we have doubled the bandwidth from 2x128 to 4x128. This provides 2x the machine learning performance. Now let's look at the memory system. So we've done lots of improvements targeting both bandwidth and capacity. We have doubled the bandwidth out of both L1 data cache and L2 cache. We also support 33% more in-flight loads and stores. And these changes help expose more memory level parallelism and performance. We've also made a lot of improvements targeting large footprint applications. So the L2 TLB is now 66% larger. The L2 capacity has grown from 512 kilobyte to 1 megabyte. Similarly, the L3 capacity has grown from 4 megabyte to 8 megabyte. So we have essentially doubled the maximum L2 and L3 capacities. And these changes help large footprint applications. So that's Cortex-X1 in a nutshell. With that, let me hand it back to Stefan.
Yeah, thanks, Jinson. So alongside X1, we've also launched in May the A78, really our most efficient premium A-class CPU ever designed, increased of 20% of sustained performance compared to the previous generation, which was A77. Now, 78 really represents the very best that we have been building in terms of premium performance at its best-in-class efficiency. And it's actually one of the answers of delivering that challenge for additional efficiencies that we want. Now, our designers have been working hard, and our design teams have been working hard to optimize all those aspects of the microarchitecture based on really not just the experience of the A77, but it even goes back all the way to A76. So really the goal was to optimize for more performance at higher efficiency. Now, in the next slides, we'll give you a bit more detail on what the design team have done to really achieve that great power efficiency, as well as this additional sustained performance. So in terms of what really the need for it was, just coming back to the very beginning, was really need to support this all-day productivity and essentially those new experiences through 5G. And that's where a need for a processor like the A76 comes in. So let me have a quick look as a reminder of what the A78 looks like. So first, let's look at the features. So an A78 is an ARMv8.2 CPUs, similar feature set in terms of cluster support as the A77 as well as the A76. However, it's smaller than A77, it's lower power and delivers more performance. As you all know, we have been working on the DSU, the Dynamiq shared unit, for a couple of generations now. So essentially, you can build an A78, plug it together with an A55 little core, and build your great big little systems that you need for your markets. In this generation specifically, what we've done is we've added support for additional cache configurations. Specifically on the L1 cache sizes, we actually went down in terms of absolute RAM area. So you can now support 32 kilobyte L1 caches, as well as essentially give you more scalability because of the additional configuration choices. Now, for a bit more detail on what the A78 looks like, let me hand it back to Jinson.
So let's dive into Cortex-A78. It is smaller and lower power and has more performance than the previous generation A77. So we have optimized all aspects of the machine, including the width and depth for efficient performance. So on the front end, we have made big improvements to the branch predictor. So in the Cortex-A pipeline, the branch predictor is decoupled from the fetch pipeline, and it's running ahead, hiding taken branch bubbles from the core. It also acts as an eyesight prefetcher, fetching lines that would have otherwise missed in the L1 instruction cache. So in A78, we've improved the branch predictor to process 2 taken branches every cycle. We've also improved the branch predictor accuracy. So these optimizations help the predictor to run ahead, further ahead, and provide more fetch bandwidth, and then even earlier prefetches into the L1 instruction cache. So area efficiency is another aspect we have focused in A78. So we have achieved this by going after large area structures that provide small incremental performance. So in other words, we have ensured there is good ROI for the area spent on various microarchitecture structures. So we've added support for 32 kilobyte L1 instruction cache, and also sized the branch predictor more for efficiency as opposed to peak performance. Let's look at the core. So on the performance front, we've added a new integer multiplier, which is doubling the integer multiply bandwidth. But most of the effort in the core was spent on power and area efficiency improvements. So let me give you some examples. We have increased the density of various microarchitecture structures like register files and reorder buffer using proprietary techniques. This allowed us to pack more operations in the same area. This translates to a larger out-of-order window or more performance for the same structure size. Another example is the segmented issue queues in this generation. This is great for timing, power, and area. We have also made improvements to the dynamic code optimization. This is the second generation in A78. This is where specific code sequences are automatically optimized in hardware to run more efficiently in the core. So we have added new instruction fusion cases. Now let's look at the memory system. So in A77 load store unit, it could support 2 concurrent load source stores every cycle. In A78, we've added a new load AGU and result bus. This allowed us to do 50% more loads in parallel. One other area where we've continued to invest is in the data prefetcher. The core has several prefetch engines that work together to prefetch lines into L1 and L2 caches. We have continued to improve the coverage, accuracy, and timeliness of these engines. We've also added a new engine specifically targeting irregular access patterns, which is worth highlighting. To improve the area efficiency, we've added support for 32 kilobyte L1 data cache, and also sized the L2 TLB for mainstream workloads. Next, let's compare the power efficiency of A78 with A77. On the y-axis, you can see spec-int total power, and on the x-axis, the spec-int performance. The A77 is shown in blue and A78 is in green. In this graph, lower is better. It translates to lower power for delivering the same performance. It's important to note that this is ISO process, so all of the benefit here is purely coming from the microarchitecture. So the key takeaways are, number one, A78 is 30% lower power at the same performance. It is 7% better performance for the same power. And it is 36% lower power at ISO peak performance. Let's move on to the performance. So here is a performance comparison of X1 and A78. This is against a A77 baseline, assuming the same process. As you can see, X1 is delivering 30% higher performance. On the other hand, Cortex-A78 is delivering 7% higher performance, but this is at lower power and area. So we have 2 excellent products from ARM here, with X1 delivering ultimate performance and A78 delivering high performance at best-in-class efficiency. With that, let me hand it back to Stefan.
Thanks, Jinson. Yeah, it's really, truly impressive work by the whole design team. Thank you very much. Now let's change gears a bit, right? So we've talked about smartphones, and they really have become our personal hub to the digital world. However, we think there's also additional technologies that our ecosystem actually will want to develop and to really enable that best user experience. So specifically, if we talk about increased computing demands, especially for systems that actually want higher core count performance, really, I think, is where we need to invest next. Another item on this is clearly security. We have been working on security essentially since the existing of ARM. And today, actually, we are proud to introduce to you guys the Cortex-A78C, which is a derivative product from the A78 to really address specific new market needs, such as large screen compute, as well as other on-the-go device form factors. So important here is we have built in new security features into A78C, point identification being one of them from the V8.3 as well, the V8.6 architecture. And also we have enabled with this upgrade another option for the dynamic shared unit that allows us to scale to larger than 4 big cores. And actually we can now scale up to 8 big cores in one DSU. So this will allow essentially big core only systems up to 8 big cores or 6 core systems, hexacore systems as well. We've also in the same update basically been working on a large L3 cache as well. So A78 actually now supports up to 8 megabyte L3 cache as well. Now, just really quickly, what does point identification do? Clearly, we are trying to avoid any of the raw return-oriented programming exploits, as well as job attacks like the jump-oriented exploits. And that's actually where point identification comes in. I'll give you a bit more details later on. Important to note, A78C has the same PPA as the A78. So whatever Jinson just presented to you guys, that's basically what 78C will present as well, besides, of course, the upgrades to the DSU itself. Now let's dive a bit deeper into what 78C looks like. On the left-hand side, you can see a typical diagram that we show for our CPUs and our clusters, and you can see an octa-core configuration. So 8 big cores in one cluster now can run into a large L3 cache. And of course, gets all the goodness of the original A78, now with the updates of A78C in the same cluster. Now, clearly, we have been working on the DSU, improving also essentially the timing of the DSU. So we've worked on additional slicing support that allows better floor planning for the DSU itself, but also really increased things like snoop filters to make sure that the performance can be sustained. Now, what does it leave you with in terms of scalability of Dynamiq? On the left-hand side, you can see the traditional mobile smartphone-oriented type systems where you can scale from little only all the way up to like a 4+4 type systems as we see today. And of course, we can actually scale in terms of those big cores, in terms of heterogeneous compute, even within that cluster to additional implementations. And on the right-hand side, you can now see the A78C type systems where you can see 6 cores, 8 large cores type systems that we'll see coming to the market. Now, that's not the only aspect. It's not just about kind of larger performance for more core count, but it's actually also about security with PAC, right? So why security is important? Just as a reminder, clearly identity protection is important, content protection, user confidentiality, all that is important. But actually what we see as well in the market is clearly a lot of AI algorithms, ML algorithms coming to the market, actually coming onto those devices like a large screen TVs as seen on here. And we want to protect those algorithms. We want to make sure they stay on the device and they don't go anywhere else. Now, for that, basically we have PAC and the point identification feature. And basically what it does is it essentially notifies the CPU as soon as there is essentially a change of a pointer happening somewhere in the system, and we can reduce the likelihood of that happening by 60% for a ROB attack and minus 40% of a job attack with point identification. So really quite exciting update from an A78 family perspective, and I want to take kind of this view as almost like a conclusion of the A78 family of CPUs. All the way on the left-hand side, you have A78. We launched it in May. My automotive and embedded colleagues have launched the A78AE. Offers great split lock support for safety critical applications, as well as also supports the same advanced security features that A78C does. And now on the right-hand side, you can see also the A78C derivative, giving you the multi-core support up to 8 big cores, larger performance because of larger caches, and the great advanced security features as well. And with that, I want to conclude and just leave you with one slide, which is what really ARM is truly focusing on in the client market, which is total compute. So total compute really is truly bringing all of the pieces that ARM provides and our partners provide together. So CPU, GPU, NPU, other system components as well as the broad and secure ARM software ecosystem that we've been building over the decades. And this solution approach, combined with the unmatched developer support and access we have, will bring accelerated growth for the future market. And we're looking forward to that. With that, thank you very much. And I'm opening up for Q&A.
Oh, great talk. And first of all, thank you guys for announcing the A78C at our conference. That when I saw that, I was like, that's an interesting piece. I didn't expect that. No, it's a huge deal. And second of all, you guys are a great tag team. You guys were in step. So we're starting. Either that's a lot of practice or you guys have worked together for a while. So we're starting to get some questions in, but sure. I'm going to be a little bit selfish and try to get one of mine in first. Can you talk a little bit more about the updates that you guys are making to your DSU?
Yeah, so let me just repeat what I've said, and then maybe Jinson, you can speak a bit more to it. So essentially, we have the DSU that we have shipped with the A76 really up to the A78. And actually, this DSU was already built in mind with having essentially additional core support. Now, we currently, and in the older days, we didn't see a need for going up more than 4 big cores. But now we actually see the need that there might be, target markets where more big cores is needed. And I think that's really where we took the opportunity and said, with the current DSU microarchitecture we have, to essentially enable the DSU itself to get more big cores in was possible in the mainline design already. And clearly we had to do work on, making sure that the frequencies still work out, make sure that the overall memory bandwidth still works out. In terms of performance as well, Sloop filter changes, but in terms of the overall structure for the DSU, already somewhat supported that, but we never really saw the need in the market. But now I think we're seeing the first step towards that direction, where larger big core counts are requested and needed. And Jinson, maybe you want to add to that?
Really quick, Stefan, can you stop sharing your screen so we can see you?
Oh, absolutely. Apologies.
I'm so sorry. Interrupt.
Yeah, one thing I want to add is, microarchitecturally, we had to increase the Snoop filter size in L3 to handle 8 big cores. So that's one. And then, as Stefan mentioned, the frequency capability, we don't want to go backwards. So we had to add some extra timing work, add some slices and so on to enable 8 big cores in a cluster. So those are the key ones. Also, the size increased to 8 megabyte. So yeah. Those are the main changes.
And something that I just wanted to kind of ask, are people beholden to using one slice of L3 cache, or is there configurability to that as well?
Jinson, you want to take that one?
Are you talking about a cluster? Do
you want to put all of those? Yeah, sometimes you can have like one big L3 cache in the middle of the chip, or maybe you can split it across different cores.
Yeah, at least in the mobile client markets, what we're seeing is it's a single shared L3 for all the cores. Sometimes they even have accelerators plugging in through the ACP port that we provide. So it's a single L3. That's primarily what we see. In the other markets like infrastructure and automotive, obviously there is a lot more system level L3 and hierarchy and partitioning and so on.
And does your new DSU support both configurations?
Yeah, so there's nothing in the DSU that prevents it from building a much more scalable SoC. So we do have cache coherent interconnect, which can be used to string together multiple clusters, and it'll all work seamlessly. Okay.
Can you speak a little bit on how the PPA of the X1 versus the PPA of the A78 compare for the same process technology node?
Yeah, so they both have the same frequency capability. As I mentioned, X1, we had to do some additional work to make sure the frequency doesn't go backwards, right? So we had to do some microarchitectural restructuring to enable high frequency operation. But on the power and area front, A78 is all about power and area efficiency. There is a lot of effort trying to optimize it and making sure it's highly efficient. X1, on the other hand, is all about performance. Power and area are sort of secondary. So we have sort of gone beyond traditional, power area budgets for A-class cores with the X1 design, right? Because it's all about pushing performance.
Okay. And for your, now that you are scaling up to higher core counts for the large cores, is this only for the A78 and A78C, or can we also use the X1 as well?
So actually, the DSU is capable of taking an X1 as well. Actually, the DSU update itself is not limited to the C version, so to speak, but we've built it with the C version in mind, so with the A78C in mind. But definitely, it will be possible to scale that with an X1 as well.
Okay, so you'd be able to get 6 to 8 big or 6 to 8 X1 cores.
Yes,
with
you could.
The new oh, fantastic.
Yes, you could.
So, can you? I know that there was a recent announcement about ARM moving to 64-bit only support. Does your current A78C support 32-bit?
Yes, they do. So actually, all of the V8.2 CPUs still support, x32, x64.
Okay. And so we've seen sometimes companies develop custom cores based on ARM architecture, and sometimes we see them also flip back. How do you expect the X1 and the 78C to drive this one way or the other?
So we expect our business model is based on collaboration and actually complementary designs, right? So you can take an architecture license, and it allows partners to build their own brand ground up designs, right? Which is, I think, a great opportunity. We provide the CXC program, the Cortex-X Custom Program, that actually allows partners to essentially go with ARM and let us implement the CPUs and then implement their custom feedback that they have, right? Which I think is it's a really good step for somebody that wants to get additional customization, but really doesn't have to do all the ground up work, right? That's basically what ARM does. So I think from a CXC perspective, definitely it will help any partner that wants to customize. 78C is really outside of that. It's really more an update to the standard roadmap that we see in the market, and we see some specific market aspects where this is interesting. And yeah, so I think it's kind of a complementary than instead of.
Okay. And I noticed with at least ARM v8.4, there's new and updated multi-OS support. Could you speak a little bit more about that, and maybe a little bit about how the A78C and the Cortex-X1 may be implementing such solutions?
Yeah, so we actually in this announcement are not talking about that. So there is additional features in the architecture, right, that are out there in the architecture itself. That's v8.4 specific, not necessarily we have to implement everything on that.
I see. Okay. And then what versions of the ISA does the X1 and the 78C support?
So X1 is v8.2, and so is A78C. It's baseline v8.2. And then additional features handpicked essentially from v8.3 and v8.6, which are around the point notification pieces.
Okay. And can you discuss, so you discussed that the X1 now features a more aggressive prefetch architecture. Could you talk a little bit more about what do you mean by more aggressive? Can you give any details? I know sometimes it's secret sauce, so anything would be appreciated.
So you take that one. Yeah, so I think prefetch, it's all about, we have, like I mentioned, we have several engines that are targeting various styles of prefetch. They all work together. So most of the time we spend on trying to have adaptive schemes, so which can manage depending on the system conditions. So one example is prefetch distance, right? So depending on the prefetch, if it's early or late, the prefetch algorithms can adapt how much prefetch to target depending on the system latency and various conditions. Another example is the throttling, prefetch throttling, right? Based on system feedback, if there is a lot more contention, then it can actually throttle back some of the prefetches to allow more demand accesses to make progress. So most of the time is spent on these sort of adaptive schemes, which can suit any of the system conditions, and then work very well.
Okay. And then at the end of the day, what are some of you touched on it, but what are some of the use cases you see for the higher large core count for the A78C?
Yeah, good question. So definitely, large screen type systems, laptops, one of them, any other kind of on-the-go gaming devices, anything that is basically kind of fits in a larger form factor than just a smartphone, especially because this is a big only type approach, right? And as well as, we can see it into industrial type PCs as well. Anything that kind of needs, literally additional big cores is where we can see it fit, right? And I think it's one of the beauties of the heterogeneous nature, right, that you can essentially use the DSU and the dynamic shared unit for that scalability.
Okay. I want to thank you for making the announcement, first of all, and then delivering a solid presentation. We really appreciate you guys taking the time and coming down here.